So let's talk about making a confidence interval for means. So I'm inventing a scenario here where I've I've had a population, I've taken a random sample, and that random sample happens to be normally distributed, or else my population is normally distributed, and I've come up with these statistics from that sample. I have a mean of 32, a standard deviation, S, remember these symbols, these are for statistics, of 15.5, and the number of items in my sample, N, was 18. And in this particular case, I want to find a 95% confidence interval. I want to be 95% confident that the two values that I get, a lower value and an upper value, that the actual population mean, remember this is just the mean of my statistic over here, that the actual population mean falls between these two values, and I have to find out what those two values are. So I'm going to start like I like to start. I'm going to start with a picture, and my picture is going to look like a normal curve, although as we'll find out as we go along in this problem, this is a T curve as opposed to a Z curve, but they look about the same, and certainly when I draw them, they look equally crummy. And right in the middle of this curve is going to be my X bar of 32, because I'm trying to find what values over here and over here bracket that 32 so that I am 95% sure that the actual population mean, whose symbol we would use, that would be mu, is between these two values. So I know that the T curve is a little bit wider than the Z curve. So I know that I'm going to have, like, one standard deviation here and two standard deviations here, and one over here and one over here. And I made my 95% a little bit wider than the second standard error, standard deviation, standard error, really. This is 1, 2, -1, -2, because I know that if I'm looking for a 95% confidence interval, it's going to be a little bit beyond two standard errors, because the T distribution is wider than the Z distribution. But you don't really even have to put in those lines, and in fact, I think for right now I'm gonna take them out. We don't really need them, so let's see if we can't get rid of them. I just wanted to give you a sense of where I think these values are gonna wind up. So I do need to find out, though, what is my standard error? In other words, what is the standard deviation, so to speak, for this distribution that I have right here? I know that the middle is 32, but I have to find what is my standard error. And I find that by using the formula. It's the standard deviation that I got from my sample divided by the square root of my sample size. This is very similar to what we did for proportions. When we were doing proportions, we did p hat times 1 minus p hat. And again, this whole thing was divided by the square root, was divided by n, and the whole thing was under the square root. Right now, the square root only has to be on the bottom. So this really here was similar to the square root of p hat times 1 minus p hat divided by the square root of n. Our denominator is always the square root of n. Why the numerator doesn't have a square root up here and why it does down here is a mathematical question that I can tell you about on the side. I don't want to get off into that right this moment. But the thing to keep in mind, though, is that the denominator on both of these is the square root of the sample size n. So to actually make the calculation, I'm going to take my S, which is 15.5, and I'm going to divide it by the square root of 18. And that gives me 3.65. 3.65. So what I want to find out is how many of these standard errors away from the mean is a 95% confidence interval. So I'm going to use the method that I used when we're trying to calculate it before. And I know that if I was way over here and went right to the middle, that would be 50% of my data. Well, to get from here over to here, I know that this is 50%. Half of 95 is 47.5%. So this number right here is the 97.5 percentile. So what I'm going to do is I'm going to go to my calculator and I'm going to say second distribution, and I'm going to do inverse t because this is a t distribution. So I go 4 and I go 0.975. Now you can't, if I just stop right there and I put the other parentheses, I hit enter, I'm going to get an error. And that's because you got to remember that the t distribution is sensitive to the size of the sample. We have this thing called degrees of freedom, df, and that is equal to n minus 1, which in this case then would be 17. So I have to go second distribution, 4 for inverse t, 0.975, comma, my degrees of freedom, which is 17, close the parentheses, and now I find out that this t value is let's call it 2.11. So it is in fact a little bit farther out than the second standard deviation that we would have for our empirical rule using these z-scores, the normal curve as opposed to the t curve. Well, now I know how many standard errors I am from the mean. I am 2.11 standard errors from the mean. So to calculate my confidence interval, I take my x bar and I go plus or minus my t asterisk. This is my new critical value times my standard error. So that's an S, standard error of my x bar. So that is equal to 32 plus or minus 2.11 times 3.65. So I've just entered that over here on the calculator, 32 plus 2.11 times 3.65. The order of operations will make sure the multiplication happens before the addition. And I hit enter, and I find out that this number over here is, let's call this 39.70. And if I just kind of go back up to there, and I want to find it minus, almost there, 1, 2, 3, I'm going to make it a minus, and I hit enter, and I get this number over here is 24.30. So that is my confidence interval, 24.30, 39.70, let's make that a nicer 4. I am 95% positive that the population mean mu is between 24.3 and 39.7. That is my confidence interval right there.